In part 1, we talk about how to realize the under circuit, like full under, half under, and how to cascade full under to realize a multiple bit under, right? So basically, we can expand this to unlimited bits, as many as you want. Okay, but today, let's try to look at how to realize a subtract circuit. If you remember, when we talk about the binary arithmetics, we said for subtraction, all the computer system, they treat subtraction as using addition. So basically, a positive number minus another positive number should equal to a positive number plus a negative number, right? But in order to do that correctly in the computer, the negative number must be converted to 2's complement form. To help you remember this, let's try to solve a very simple question quickly and see how we do this by steps. Okay, so let's try to calculate 3 minus negative 4 using 4-bit signed binary number. First, we need to find the representation for these two numbers, 3 and negative 4. For 3, we have 0, 0, 1, 1. For negative 4, first we need to write the positive 4 here. Then take 1's complement of this, and 2's complement. Okay, so 1, 1, 0, 0 basically represent negative 4. Then we add these two numbers together. We will get 1, 1, 1, 1. Then we got this result. But how do we know this is the right representation for negative 1? Here's how to check. First, the sign bit is 1, which means it's a negative number. Then we take the 2's complement again. So first 1's complement plus 1, we get 2's complement. And this tells us the magnitude of this number, which is 1. So which means this number corresponding to negative 1. So that's the steps how we solve a subtraction using 2's complement form. Okay, now we know that how to calculate this by hand, but how would the hardware treat this? So let's look at it. Here I just show you the picture of the ANDer and the subtractor circuit inside a calculator. So here we can see the main thing is the microchip, which is a 4-bit ANDer, same thing as we talked in part 1, using 4 different 4-ANDer, cascaded them together, so we can form a 4-bit ANDer. And we have some XOR gates, and in this 4-bit ANDer, we have the data A and data B, that's the input, data input, and we have a control input, which is collect to the carry in C0. For output, we have the carry out, which is C3 here, and we have the sum output S3 to S0. Okay, and one more thing about this input here is called and bar slash / sub. So you will see this type of naming strategy throughout this chapter, like talking about the modular circuit. They named those signals this way because this can tell us some information about that input or output. It will tell us the active levels and the corresponding functions. For example, in this case, it's called AND bar first, which means we know bar means not, but in here we don't say not, it means complement or active low. Okay, so AND bar basically tell us if we input a 0 in this line, this circuit will do addition. The other way, if we input a 1, you see sub has no bar on it, which means if we put a 1 on this line, this circuit will do subtraction. Okay. Now let's see how this circuit works to solve our problem. Let's first try an easy one. Say 3 plus 4. We know the answer is 7. But how does the calculator works? Say, when we do that, first we press number 3 on the keyboard, right? And this will generate the 4-bit binary number for 3, which is 0011. So basically you will see 0011 here. And then we will press plus on the keyboard. This will set the AND sub input to 0, which means this time we're doing addition. Then we will press the second operand, which is 4 on the keyboard. This will set the B3 to B1, B0 to 0, 1, 0, 0. Okay? Now, because this line is 0, and so those 4 XOR gate, they act like buffers. If you remember the truth table for an XOR gate, we have 0, 1, 1, 0, right? So if one input is 0, let's look at this too. You will see Y kind of following B, right? So basically means the D3, D2, D1, D0 here should equal to B3, B2, B1, and B0 respectively. Okay, then this ANDer, it will do nothing, just add the data A to data B and C0 together to give us a result. So in this case, we have A3, A2, A1, A0 equal to 0, 0, 1, 1. And D3, D2, D1, D0 equal to 0, 1, 0, 0. And C0 equal to 0. So the result is 0, 1, 1, 1, which is positive 7 in decimal. So that's how the calculator works. And by the way, the result 7 will be shown on the display using another modular circuit we are going to talk about, which is the decoder. Use that circuit so we can see the 7 on our screen. Okay, now for subtraction. When we want to use our calculator for subtraction, we first press the first operand, which is 3 here, right? So this is the same as addition. But the second step, we need to press minus sign on the keyboard. Now this time, it will set the AND bar / sub input to be 1, because we are doing a subtraction. Right? In our mind, we are doing subtraction. In the computer system, it's doing addition. But we don't know. In our mind, we still follow our logic. So we are thinking we are doing a minus there. Then we press the second operand 4 on keyboard. Then it will generate the binary number for positive 4, 0, 1, 0, 0. Now, so let me use blue. So blue gets 1 here. So we still have this 2 number here. But now we got 1 at one end of the XOR gate. So if we check these two combination, we can see that Y is always the opposite of B, which means D3, D2, D1, D0 should equal to the opposite of B3, B2, B1, B0 this time, which is equal to 1, 0, 1, 1. Remember what is this? This is actually the 1's complement of positive 4. Right? Then the 4-bit ANDer still is a function to add things up. It still do the same operation. It will add data A to data B and C0. But because the D3, D2, D1, D0 equal to the opposite of B3, B2, B1, B0. Okay, so we are adding 0, 0, 1, 1 to 1, 0, 1, 1. Then plus 1, because this time this C0 receive a 1 there. Okay, so think about it. What is 1, 0, 1, 1 plus 1? 1, 0, 1, 1 is 1's complement plus 1. Basically, that's the 2's complement of positive 4, right? So it's representing negative 4. So basically, this chip now is doing the operation 3 plus negative 4 here. And the result is negative 1, just as I showed you in previous slide. Okay, so that's how this circuit works. So we use one circuit to do two kind of operation, addition and subtraction. We can use another kind of more complicated example to show you the principle again. So let's look at this. So now we are trying to do two operations still. First is 45 plus 58. Now we're using 8-bit adder and subtractor circuit. So nothing different as before, excepting we have more bits. That's all, same operation. So when we have to do addition, what will happen to the and bar slash sub input? It'd be 0. 0 means addition, right? So A7, A0 would be our first operand. That's 45. So let's convert 45 to binary. That's 32 plus 8 plus 5. 6, put it to 8. Okay. Then B7 to B0 would be our second operator, which is 58. 58 is 32 plus 16, that's 48, then plus 10. Double check. So 32 plus 16, 48, 56, 58. Okay. Then because this line is 0 right now, so the delta D basically equal to delta B. So it's the same as B. Then the result is being A and D added and this added together, but this is 0, so we just add this 2. So you get 1, 1, 1, 0, 0, 1, 1, 0. So the result is 0, 1, 1, 0, 1, 1, 1. So what's the decimal value of this? Let's check. So it's 64 plus 32 plus 7. So which is 96 plus 7. That's 103. That's the correct answer, right? Now the second operation, we're doing subtraction. For subtraction, we need, after we press the minus sign, the add bar sub will be set to 1. So mean doing subtraction. And this time A7 to A0 should be the binary representation of positive 40. 40 can be written as 32 plus 8. That's 40. Then B would be the binary representation of positive 54. So that's 32 plus 16, then plus 6. Now, because this time this line has 1 here, we know D should be the opposite or 1's complement of B. So D should be 1, 1, 0, 0, 1, 0, 0, 1. Now we need again add these 3 together because that's what the 4-bit ANDer do. It adds this to that and that together. So 1 plus 0 plus 1, we got carry. So 0 plus 0, don't forget the carry. And we got 0, we got 0, we got one here, we got one here, one here, one here. So the result equal to that. But how do we know this is the right answer? Again, because this is a sign bit, which means this is a negative number. So we cannot tell the magnitude directly. We have to do 1's complement form first, then plus 1 to get the 2's complement. Okay, now we can know the magnitude, which is 14. So this number represents negative 14. Is that correct? Yes. And we can add more function to our AND subtractor circuit, like the overflow detection. This is kind of also important because we need a circuit to tell us the result is wrong, it's overflowing. Actually, you can see this in your calculator sometimes, right? If you input some ridiculous number there, you could see overflow. If you recall what we talked about overflow, we know that overflow happens if the two operands have the same sign, like a positive plus positive or a negative plus negative, right? In mathematical view, we know it's because the result go beyond the range that can be represented by the binary number. But the phenomenon we see is that the sign bit flipped. So the sign bit of the sum is flipped compared to the sign bit of the two operands. Okay, so we can use this property to design a circuit to detect the overflow. So let's see here, we have the sign bit for data A, sign bit for data A, and the sign bit for the sum. All we have to do is to compare those three sign bits, right? So take these three as input for our circuit. So we have 8 combinations. Okay. Now when there is an overflow, when the sign bit of the sigma is flipped of this result, basically this is the sign bit of the result is flipped when compared to the input data, right? So like I have 2 positive and the output is positive, that's not overflow. If I have 2 positive number but we receive a negative result, which means we got an overflow here. Similarly, if I have 1, 1, then I get a 0 here, which means I have overflow. So all other cases, we actually no overflow at all. Okay, then we can write a Boolean equation. You can use the color map, or we can directly write it here. So OV will actually equal to SA prime, SB prime, and S sigma, or SA, SB, S sigma prime. Okay. So here shows you how we can add this overflow detection function or circuit to our original AND subtractor circuit. So A7, B7, and S7 basically are the sign bit of the first operand, second operand, and the result. Okay, so here is the output of our overflow detection. Yeah. Okay, that's all the basics about the arithmetic circuit. If you like my video, please help share and subscribe, and I'll see you next time.